All right, we are live. We're going to give people a couple moments to come rolling in, but we are excited to get started with this calculus office hour. It's one of my favorite hours of the week, where we're going to be answering all of your questions about your calculus class, giving you tips and tricks to be successful on the AP exam or in your college calculus class or whatever calculus class you're in. Might even do a little differential equations along the way. So as we get started, I am so excited to see everybody here. Actually, let me pop over to this screen so that I can see your comments. Excellent. So a big hello there. Let me try that sentence again. A big hello to everyone who's rolling in right now. Welcome to this live office hour for calculus, brought to you by Chegg. I'm at Wallace STEM. You probably recognize me from my channel at Wallace STEM, where you can see me making memes and trends about mathematics. Come for the memes, stay for the math is my tagline. It's a lot of fun there, so you can check me out there. But today we're going to take some time to just review calculus with you. So hello to Abdallah12. Welcome, glad to have you here. And for everyone else who's here, if you've been here before, welcome back. If this is your first time, this live office hour, the goal here today is to help you understand your calculus courses and concepts better. I am here each week to do just that. You can think about this as your virtual office hour. I'm here to help with any questions you have, so don't be shy. Stick those questions in the chat. And I already see one question coming in. So I was going to kick things off with some trig substitution, but why don't we start with some improper integration first? Because that's coming in from Instagram, and then maybe we can do some second order differential equations after that. So first, improper integrals are just any integral that's going to have an infinity as a limit. Let's say we're integrating from 1 to infinity x e to the negative x dx. The problem is we can't actually do math with infinity. So we're going to kind of cheat and use something from what we saw at the beginning of our calculus study. We're going to use the limit, and we're going to take the limit as this upper guy approaches infinity and see what happens, see if we've got any asymptotic behavior. First, we have to actually integrate this. I'm going to probably use integration by parts because we've got a nice product that's going to work really well with integration by parts. So if I make u equal to the x, and the dv equal to e to the negative x dx, the derivative of u is dx, and the antiderivative of dv is negative e to the negative x. And then we're ready to actually use the uv minus the integral of v du. If you speak English, ultraviolet voodoo is a common thing. I hear to remember it. If you speak Spanish, I hear them say una vaca vestido de uniforme to remember it. I just like to remember spatially. I'm going to multiply that diagonal u times v, and I'm going to subtract the integral of v du. That helps me remember it. So we've got x times negative e to the x, which is negative x e to the negative x, minus the integral of negative e to the x times dx. Well, the negative times the negative will make it positive. And then we've got e to the negative x dx, and we're still integrating from 1 to infinity. The nice part about integration by parts is it simplifies the integral, hopefully down to something that we can integrate. This time, sure enough, it does exactly that. So we've got negative x e to the negative x. This comes out to negative e to the negative x, and we're going to integrate that from 1 to, I'm going to call it b. The reason I'm going to call it b is we're actually going to take the limit as that b goes to infinity when we evaluate this. So let's see what happens when we plug it in. It might be easier actually to express this. I'm going to come up here just for space. These e to the negative x's, it'll be easier to get an idea of what's going on if we drop them down to the denominators. So I've got negative x over e to the negative x minus 1 over e to the negative x. Oops, not negative anymore. Moving it down makes it a positive exponent. That's the whole reason we did that. And we're going to integrate from 1 to b. Well, when we plug b in, remember b is going to approach infinity. If we put infinity in here, we get infinity over e to the infinity, which is infinity. So we might need to do a little bit of L'Hopital because the numerator is going to infinity and the denominator is going to infinity. So if I take the derivative of the top, I get 1. The derivative of the bottom is e to the x. And now I can see if I make this exponent go to infinity, sure enough, this is going to go to 0 because we get 1 divided by huge. So this first term gives us negative 0 minus, again, 1 over e to the infinity also is going to go to 0. Then we're going to plug this lower limit in, change the subtraction to addition because we're subtracting a negative. 1 over e to the first is 1 over e. plus, because we're subtracting a negative, plug the 1 in. 1 over e to the first is 1 over e. And if I combine my terms, we get 2 over e is the area underneath this curve from 1 up to infinity. So that's kind of how I would do an improper integral. Excellent. We've already got a lot of great questions coming in. We're going to do our best to evaluate as many of them as possible. We got a question for some higher order differential equations. Now, there's a lot of ways that we can work with higher order differential equations, and I don't want to get into the detailed meat of it. So let's kind of just do a really brief introduction to second order differential equations. Let's say we've got the differential equation x prime prime minus x prime minus 12x equals 0. Just a really basic differential equation of second order. Means it's got second derivatives with constant coefficients. So there's no x's or y's as coefficients. What we can do to help us solve this is, instead of solving it as a differential equations, we're going to actually solve the auxiliary equation that comes from it. In other words, we're going to take the second derivative and treat it like a second power. The first derivative we're going to treat like a first power, and the 0th derivative we're going to treat like a 0th power, because that's going to give me an equation that we know how to solve from our algebra days. We can just factor this equation to get m minus 4 times m plus 3 equals 0. And solving tells us that m is 4 and negative 3. That helps us know the form of the actual solution to this differential equation. The solution to this differential equation is going to be x equals constant times e to the 4t plus another constant times e to the negative 3t. This equation, we don't know what C1 and C2 are. We could solve them if we had some initial conditions. But this equation is a solution to this differential equation. What does it mean to be a solution to a differential equation? That means if I plug this in for x, and also the first and second derivative, let's find those really quick. The first derivative of x is 4c1 e to the 4t. The first derivative of this term is negative 3c2 e to the negative 3t. And we have a second derivative on there also. So let's take the second derivative. 4 times 4 is 16 c1 e to the 4t. Negative 3 times negative 3 is a positive 9 c2 e to the negative 3t. So if I plug this in for the x, and I plug this in for the x prime, and I plug this in for the x double prime, hopefully that's going to give us 0 for an answer. Let's find out. Starting with x double prime, so we've got 16c1 e to the 4t plus 9c2 e to the negative 3t. Then we're going to subtract x prime. That's the second one. So we're going to subtract 4c1 e to the 4t. Subtracting a negative gives us a positive 3c2 e to the negative 3t. And then we're going to subtract 12 times this second equation. So I'm going to multiply this, first equation. I'm going to multiply this first equation by negative 12, which will give me negative 12 c1 e to the 4t. I know I'm going off screen, but the equation's still here where you can see it. And negative 12 c2 e to the negative 3t. And let's see what happens when we combine like terms on this expression. Let's go with the light blue to do that. So on the e to the 4t's, we've got 16 minus 4 minus 12 gives us 0. On the e to the negative 3t's, we've got 9 plus 3 minus 12 gives us 0. So yes, my solution here, this red one here, is actually the solution to our second order differential equation. That's what we're doing with differential equations. All right, great question with the second ordered differential equation. I've got a request to solve an integral of 1 over 1 plus x squared. let's take a look at that, and let's really dive deeper into it by doing it with trig substitution. Because the integral of 1 over 1 plus x squared dx, make sure I'm looking at that right. It was x squared, not cubed, right? Yeah, x squared. This is a formula. It's tangent inverse of x squared. But why is it tangent inverse? Where does that come from? It actually is going to come from a simple trig substitution, which is really nice. Trig substitution often generates a lot of questions. So maybe if you want to see another trig substitution problem that's a little more involved, let me know in the chat and we'll dive into it, take a look at it. The idea of trig substitution is I can make a trig ratio that's going to make this part into a trig identity. So if x was tangent of theta, dx then becomes secant squared theta d theta. Okay, so when I make that substitution, the problem is going to become the integral of the dx, which is secant squared theta d theta, over 1 plus x squared, which is tangent squared of theta. Well, the nice part about 1 plus tangent squared is 1 plus tangent squared can be replaced with secant squared. That's that Pythagorean identity. So instead of 1 plus tangent squared, we have secant squared, and secant squared over secant squared reduce out. So really, I'm just integrating d theta, which is just a theta plus c. So what is theta? Well, if I go back to my original problem, if tangent of theta is equal to x, I could take tangent inverse of both sides, and that's equal to theta. So this is equal to tangent inverse of theta plus a constant. And that's why we have that formula that this equation comes out to tangent inverse, or arctangent, as a lot of people like to call it, because that -1's a little confusing. It is not an exponent. It does not mean reciprocal. And so some people prefer to call it the arctangent as well. It depends on your textbook, really, what you're going to see. All right, got lots of great questions coming in. Since we just did a trig substitution, let's do another trig substitution, the one that's a little more involved. It's got like that square root in the bottom that Connor on TikTok wants to take a look at. So let's do that right now. By the way, if you're new to us, welcome. This is Cheg's office hour for calculus. I'm answering all your calculus questions that we can answer in this hour. So if you have any questions, stick them in the chat and we'll do our best to answer as many of them as we can. Let's do the integral. I'm going to break the rules a little bit. You wanted the square root in the bottom. It doesn't actually matter where the square root is. So I'm going to put the square root on the top this time and do the square root of 9 minus x squared over x dx, because this trig substitution is a little bit more involved than the one that we just did, but it's going to have a lot of the nice same benefits. And by that, I mean it's really nice that we can make this inside the square root into a trig identity that we can take the square root of, and then everything will simplify really nicely. Let's give it a go and see what happens. So we've got the integral. Oh, wait, I got to say what my substitution is. Oh. What is x equal to? To decide what x equals to, we take the square root of the number hanging out with x squared. So the square root of 9 is 3. And then if it's subtraction and the variable is last, we do a sine of theta, because we want to make this into 1 minus sine squared. If the x was first, we would make it secant, because then we want to have secant squared minus 1. If it's addition, the order doesn't matter. We're going to make it tangent squared, because we want to have tangent squared plus 1. So we want 3 sine this time. dx, then its derivative is 3 cosine theta d theta. So let's rewrite our integral, making that substitution. We've got the 9 minus x squared. If I square x, we get 9 sine squared of theta times dx, which is 3 cosines of theta, d theta, all over an x, which is 3 sine of theta. What's nice about this is if I look at this square root, we can factor a 9 out, and take the square root of 9. The square root of 9 is 3. Yeah, we're just going to rewrite it. I was going to try it right over. Once I've taken the 9's out and taken the square root to get 3, what's left is 1 minus sine squared. 1 minus sine squared is cosine squared. Is cosine squared, the square root of cosine squared is just cosine. Times 3 cosine over 3 sine. Well, this is nice because we can reduce out one of the 3's. And we're going to end up with a 3 times the integral of cosine squared theta over sine of theta d theta. What are we going to do from there? Oh, I know what we can do from there. We're going to use another trig identity and split up this cosine squared because cosine squared is 1 minus sine squared. So let's rewrite this as 3 times the integral of 1 minus sine squared all over the sine of theta d theta. Why is that better? Good question. The reason it's better is because now I can take this sine of theta and I can divide it by both terms. I can't just reduce it with one term, but I can distribute it and divide by both terms, which gives me the integral of 1 over sine. The reciprocal of sine is cosecant. Minus sine squared over sine gives me a single sine. And then we can actually do the antiderivative of this expression. We've got a 3 out front. The antiderivative of cosecant is the natural log. Actually, it's a negative natural log. Cosecant plus cotangent. Minus the antiderivative of sine is cosine. Actually, it's positive cosine because the derivative of positive cosine is negative sine plus our constant. This gives us a solution now in terms of cosine. Was there a question there? Couldn't we also draw a right triangle to visualize? Yes, we are actually going to do exactly that on our next step here. So here's our right triangle to kind of visualize what's going on. Here's my angle theta. And if I divide both sides by 3, we find out x over 3 is equal to sine. Well, sine we know is opposite over hypotenuse. So the opposite is x, the hypotenuse is 3. The adjacent is the square root of 9 minus x squared using the Pythagorean theorem. We can do that now to plug into this and evaluate what we end up with. So we have 3 times negative natural log of the cosecant. Well, cosecant, reciprocal of sine. Sine is opposite over hypotenuse. This is hypotenuse over opposite. Hypotenuse over opposite, 3 over x. Plus cotangent. Cotangent is adjacent over hypotenuse. That's the square root of 9 minus x squared over x. It's nice that we have a common denominator. We could rewrite that with a common denominator if we wanted to. Plus the cosine. Cosine's the adjacent over the hypotenuse, which is going to be the square root of 9 minus x squared over the hypotenuse of 3 plus our constant. And then we could go through and do a little bit of simplifying here if we wanted to. I could distribute the 3 through, combine these to have a common denominator. So we have negative 3 natural log of 3 plus the square root of 9 minus x squared all over x. Plus 3 times divide by 3, that's just going to leave the square root of 9 minus x squared plus our constant. We'll call that our finished product. That is a great one to kind of help see and visualize what's going on. Excellent. Great questions. Hey, can you evaluate 32 times the antiderivative of that? That looks like some partial fractions, maybe. If not, we're going to do some tangent inverse. Let's do that one next. We got a question from Instagram with Nadim Shaki. Let's take a look at that one. Keep those questions coming in the chat. Even if I haven't answered it yet, it might be on the waiting list to get to as soon as we can. So keep those questions in there as well. So I'm going to see if I can copy this correctly. It is negative 32. That's kind of random to have in front of a radical, but okay. Times the antiderivative or the integral of x minus 19 over 5x squared minus 14x minus 5 dx. All right, that looks like a fun one. Hopefully, this is going to factor nicely and give me some partial fractions. I think it does. 5x squared is 5x times x. 5 is 5 times 1. And a nice tip when factoring is you can never have a common factor inside of a factor. So I know I can't put the 5 here and the 1 there because they both have a 5. That doesn't work. So this is the only possible thing that could work. And it doesn't. Well, that's a bummer. All right, we're going to need to go plan B with it. So partial fractions do not work. I did it wrong in my head. That's okay. We can still get at it. Let's see if we can manipulate this so that we can use a u substitution. Let's see if we can make u equal to 5x squared minus 14x minus 5. That way this entire denominator will become my u. If that's the case, du is going to be 10x minus 14 dx. I don't have 10x minus 14. Well, let's try and get 10x minus 14. We're going to actually try and force 10x minus 14 into this expression. And the first thing I have to do is multiply it by 10. If I multiply by 10, I have to divide by 10. That's going to give me 10x minus 190. We don't want minus 190, we want minus 14. So what I'm going to do is I'm going to actually split this 190 up. So we have 10x minus 14 minus 176, because 176 and 14 would give me 190. The reason I'm going to do that is that's going to allow me to take this denominator and divide by the 10x minus 14 and the 176 separately. So let's see what that gives us. We've got negative 32 over 10. That's going to reduce, divide by 2, 16 over 5. Still don't know why that number's there. That's kind of random. Times the integral of, we're going to do the 10x minus 14 over the 5x squared minus 14x minus 5 dx. Plus, actually I'm going to say minus, we've got the 16 over 5. I'm going to distribute that through times a separate integral for the negative 176 over the 5x squared minus 14x minus 5 dx. Now this first integral is really nice and easy. It's just the natural log of the denominator. That's how we built it with the du. The second integral is going to take a little bit of work, but we can change it, hopefully, into a tangent inverse. Nope, it's not going to be a tangent inverse. Let's see. Well, let's see what happens when we complete the square on this part. So to complete the square on this part, first I want that x squared to be by itself. I don't want that 5 there. So I'm going to factor the 5 out. So that's going to make this part negative 16/5, actually 20/5, integral of negative 176. And that constant could come out, actually. Let's do that. Make it a plus 176 times 16, whatever that is. 1 over, we factor a 5 out, we get x squared minus 14/5 x minus 5 dx. Boy, did you make up this problem just to give me a headache? This is a little bit more involved than I thought it was going to be. So now what we can do is we can complete the square by focusing on this part of the problem and taking half of this middle term, which is going to be 7/5, and squaring that, which will give me 49 over 25. But if I add 49 over 25, I have to also subtract 49 over 25. And so now when I do that, we're going to end up with whatever 176 times 16 over 25 is, times the integral of 1 over x minus 7/5 squared minus 25 and 49 is 74 over 25 dx. And then my guess is you've probably got an integral table formula for this one here that you'd be able to look up and solve from there. So I'm going to stop there because that's in the form. The integral table that you're looking up, you want the integral of 1 over u squared minus a squared du. That's going to be in your integral table, and you can look that up and solve it. We could solve it by trig substitution, but that's going to take another 5 minutes, and I want to get to some of the other questions. But hopefully that gives you an idea of how we can get started on this one. That was probably the most involved problem we've done on one of these calculus lives. So thank you for asking that one. Let's see what other questions we have coming in the chat, because this is your office hour to answer all of your questions. Oh, I didn't factor the 5 out of the -5 in the denominator. You're right. That should have been a -1. Good catch. Good catch. Exactly right. Excellent. Excellent. Yeah, I didn't factor the 5 out of the -5. Thank you for pointing that out. Sorry about that error. Let's use partial fractions for the next one. That's a great idea on TikTok coming in from @Simbonelobroski. Yeah, let's do some partial fractions. Let's do one that actually works as partial fractions and can factor. Let's do the integral of x minus 9 over x squared plus 3x minus 10 dx. So that we can actually practice that process of partial fractions, because it's probably one of the most important integration methods we have, because it comes up a lot in some of our future math classes like differential equations and the like. The idea of partial fractions is we want to split this fraction up into 2 fractions where each fraction has an easier integral. So let's factor out the denominator. X squared is x times x. 10 is 2 times 5. And if the 5 is positive and the 2 is negative, we definitely get that 3x in the middle. So we're going to split this fraction up into some number over that x minus 2 factor, plus another number over that x plus 5 number. And we want to make sure it's equal to whatever x minus 9 over x squared plus 3x minus 10 is. So let's solve this equation. Multiplying by the denominator, the x minus 2's will reduce out, leaving just a times in x plus 5. When we multiply the second fraction, the x plus 5's reduce out, leaving just the x minus 2. And after the equal sign, both of them will divide out, leaving just x minus 9. This is going to give us an equation that we really enjoy because it is true regardless of what x is equal to. So I can pick any value for x I want. Let's say I want x to be 2. Why did I pick 2? The reason I picked 2 is it's going to make this term go to 0, because we have 2 minus 2, which is 0, times b, which is 0. So I just have 2 plus 5, which is 7. 7 times a is equal to 2 minus 9, which is -7. Divide both sides by 7, and I can see a is -1. Let's do the same thing to find b. To find b, I want the other one to go to 0. So if x is -5, -5 plus 5 is 0 times a is 0. This one's gone, and I'm just left with -5 minus 2 is -7b is equal to -5 minus 9 is -14. Divide both sides by -7, and b is equal to 2. Which means while this integral might look really crazy and hard to solve, we can split it up to the integral of a, which is -1, over x minus 2, plus b, which is 2, over x plus 5. And this integral is the exact same integral as the other one, but we've broken it up into 2 fractions. And it's really nice because each fraction is easy to take the antiderivative of. It's just the natural log of the denominator, plus 2 natural log of x plus 5. And of course, don't forget to do the plus c to finish off that problem. So that's how I would do the partial fractions. Hopefully that is helpful. What if x minus 9 were x squared minus 9? Right here? If this was x squared minus 9? Good question. Let's take a look at that. I like that question because it's going to make this problem a little more interesting. I'm going to slightly change our strategy, and I'm just going to get through the setup because the second half is identical. It's still the partial fractions, but the first half is a little different if it was x squared minus 9, because now you've got x squared on both numerator and denominator. Partial fractions only works if the denominator has the higher power. Here, the numerator has the same power. So we're going to fix that by doing a little bit of long division. We're going to take this denominator of x squared plus 3x minus 10, and we're going to divide it into x squared plus 0x minus 9. And it's important to note we need to make sure every value of x is accounted for here. So we've got x squared, x to the first, x to the 0. And then when we divide these, we divide the x squared by x squared, and we get 1. Then I'm going to multiply the top number by the front. So 1 times x squared is x squared, 1 times 3x is 3x, and 1 times negative 10 is negative 10. And then, just like regular long division, we subtract this. But make sure you distribute that negative all the way through, changing the signs. And when I do, the x squareds are gone, and we get negative 3x plus 1. This negative 3x plus 1 now has a smaller exponent, so this is my remainder. We can write this as 1 plus a negative 3x plus 1 over the front thing, which is x squared plus 3x minus 10. So now I'm going to integrate the 1 dx, and then I'm going to also integrate the negative 3x plus 1 over the x squared plus 3x minus 10 dx. What's nice is this first one, the antiderivative of 1 is just x. And then we have to solve this one. And the way we solve this one is by the partial fractions. And so we would go back through the partial fractions using the exact same method we solved in the other process. We factor it, a over this, b over that, see what values for a and b, and then we get the natural log of the first one, natural log of the second one, and of course, don't forget the plus c. So that's what we would do if the exponent was bigger or even the same in the numerator. Question from Lucas is, do we want to combine the logs into one natural log at the end? It really depends on your instructor. If you are in AP Calculus, the answer is no. In AP Calculus, you want to do as little simplifying on the free response questions as you can, because they will give you full credit for a correct, unsimplified answer if you've done the calculus. But if you make a mistake while you simplify, they will dock you down for those mistakes. So when you get that safe stop on the AP test, stop. If you're in a regular college calculus class, run-of-the-mill class, ask your instructor what your instructor wants. Do whatever your instructor wants. Excellent. Excellent, excellent. Can I explain U substitution with an example? I'd love to do some U substitution. Let's do that. Oh, but before we do, where did the negative come from? What negative are you talking about? Are you talking about when we subtracted here? That just comes from regular long division. You always multiply and then subtract whatever you get. So that's kind of the long division algorithm that you learned in elementary school. Didn't know it was going to be so useful for calculus, but sure enough, it is. All right, had a request for some U substitution. So let's do some U substitution problems. Let's do the integral of, let's do e to the 3x over e to the 3x plus 5 dx. What we're looking for in U substitution is we are looking for a problem or a factor where the derivative of part of the problem is multiplied by the dx. Notice if I look at this denominator, if I were to make that all u, e to the 3x plus 5, its derivative, du, would be e to the 3x, and then the chain rule says multiplied by 3 dx. Well, we have e to the 3x dx, we're missing the 3. But what's really nice about a constant, and you can only do this with a constant, don't try to do this with a variable like sine x or x squared or x cubed, you can't do that. But when I've got a constant, you can multiply by the constant inside and outside, because constants can move in and out of the integral. X's cannot, so that's why we can't do it with X. But 3 times 1/3 is 1, so we haven't really changed the value. So now we've changed this problem to an integral that's got a 1/3 out front. The 3 e to the 3x dx all became the du, leaving nothing left in the numerator, or a 1. We need a placeholder. And then this e to the 3x plus 5 all becomes a u. And this will simplify the problem down to an integral that's much easier to work with. So we've got 1/3. And the antiderivative of 1 over the u is the natural log of u, of course, plus our constant. But you're not officially done until you go back to the original value, because remember this u, I should have made it a blue u actually. This u is the u of e to the 3x plus 5. So my answer is going to be 1/3 natural log of the u plus c. So what is u? E to the 3x plus 5. And so that's going to be my final solution. Excellent. We got a question, looks like a little differential equations application in population. So let's see if we can take a look at solving your dy dx equals ky and solving that differential equation. All right, you got dy dx equals ky. And k is just a constant, y is our variable. And these is what we call a separable differential equations. These do come up on the AP Calculus test. The way a separable equation works is we're going to treat the dy dx like a fraction, even though it's going to freak your math teacher out when we say that. We're going to treat it like a fraction, and we multiply both sides by the dx. Then we'll have our dy equals ky dx. The idea is we're going to separate the variables, and we want the y's on the side with y and everything else on the side with x. Well, if I divide both sides by y, I get 1 over y. dy is equal to k dx. Now that dy and dx have been separated, we're ready to integrate both sides to see what that gives us. So we'll integrate the 1 over y, and we'll integrate the k on the left with respect to y, on the right with respect to x. Integral of 1 over y is the natural log of y. The integral of k is kx plus a constant. And technically there's a plus c on both sides, but if you subtract one from the other, we get a different constant. So we can just absorb all the constants into that plus c there. All right, usually we want to solve the equation for y. So to do that, we're going to exponentiate both sides to get rid of the natural log, leaving just y equals e to the kx plus c is the same as e to the kx times e to the c. And e to the c, e is a constant, c is a constant. That's just going to become a different constant. So let's call it a capital C representing the whole constant, e to the kx. And that is the solution to our differential equation. And I think that's the form that you wanted. I think you used A instead of C for your constant. But that's the same exact idea for that population growth. Somebody's asking about e to the pi I equaling -1. E to the pi I equals -1. Yeah, that comes from a Taylor series, actually. So let's do a quick look at Taylor series and what they tell us. So the idea of a Taylor series is, let's say we've got e to the x. I can list several derivatives of e to the x. The derivative of e to the x is e to the x. The derivative of e to the x is e to the x. The derivative of e to the x is e to the x. Let's actually call this, that's f. This is the first derivative. This is the second derivative. This is the third derivative, and there's an obvious pattern here. And if we wanted to build the Taylor series centered at 0, that's probably the easiest way to go. It's also called the Maclaurin series when we center it at 0. If we center it at 0, we're going to evaluate at x equals 0. So f of 0 is e to the 0, which is 1. F prime of 0 is e to the 0, which is 1. F prime prime of 0 is e to the 0, which is 1. And f prime prime of 0 is e to the 0, which is 1. I told you we started with the most basic case. We'll look at sine and cosine in a minute. They're a little more complicated. The idea of the Taylor series, though, is the function e to the x is equal to the sum as n goes from 0 to infinity of x to the n times f, we'll say sub n of x, or the center, so in our case the center is 0, divided by n factorial. So in our case, what that's going to be is the 0th derivative at 0 was 1 times x to the first, which is x, over 0 factorial, which is 1. Plus, whoops, let me back up. I got ahead of myself. We're starting at n equals 0. So the 0th derivative is 1 times x to the 0 power, because we're doing 0th derivative, over 0 factorial. Plus 1 times x to the first over 1 factorial. Plus 1 times x to the second over 2 factorial. Plus 1 times x cubed over 3 factorial, and so on and so forth and so on. And you kind of start to see the pattern here. This expression has changed e to the x into a polynomial function that we can use and work with. So that's kind of the idea of Taylor series. With sine and cosine, because of the cyclic nature of those functions, they end up coming out to having 2n plus 1 or 2n as exponent. I think it's 2n minus 1, actually. But then you can combine the sine and the cosine functions to get e to the x, and you end up with the nice little formula. If you combine the sine and the cosine function to get e to the x, you find out e to the theta times I is equal to the cosine of theta plus I sine of theta, which is kind of cool. I'll let your calculus teacher give you the full proof where you add the cosine and sine Taylor series together. It equals the Taylor series for cosine and sine times I. But what's really cool then is if theta equals pi, we end up with e to the pi I is the cosine of pi plus I sine of pi. And the cosine of pi is -1. And the sine of pi is 0 times I is 0. And so we end up with e to the pi I equals -1, or e to the pi I plus 1 equals 0. That's just kind of a fun result, combining all of these complex irrational numbers together to get a beautiful answer of 0. It's a fun consequence of Taylor series. It's not really a major topic of calculus, but it is one that kind of comes up when you're talking about Taylor series. All right, you got me digressing about some of the fun corners of calculus. Let's take a look at doing an integral involving secant and tangent to different powers. I don't know that I have one handy, so let's make one up. Hopefully it doesn't get ugly. Let's look at the secant cubed of x times the tangent to the 5th of x dx. When we're dealing with integrals of secant and tangent to different powers, what we're going to want to do is make a u substitution. But we're not quite sure which u substitution we want to make. Some people like to memorize all of these rules. If exponent on secant is odd and tangent is even, then you do this. But if tangent is odd and secant is odd, then you... So many rules. Let me show you the easy way to do it so you don't have to worry about the rules. There's two options. You're either going to make u equal to the secant of x, or you're going to make u equal to the tangent of x. Sometimes they both work. Usually one of them works. You just have to figure out which one works. So let's just try one. Let's see if secant works. If u equals secant, du then is secant x tangent x. Actually, just for the sake of explaining it, I'm going to show why this one doesn't work first, and then we'll do the one that does work. I had them backwards in my head. So if u is tangent, du is secant squared of x, dx, x, not theta this time. So that means I need to pull off a secant squared to go with the dx. So I'm going to pull off a secant squared to go with the dx. When I do, I'm left with a secant x to the first power. When I do that, secant squared x dx, that's all going to become my du. We want to know, is it possible to make the rest of it into tangents? Well, I've just got a secant. I can't make secant into tangents. That's just not possible. I could make a secant squared using the Pythagorean identities, but it's just not possible to make that substitution. So we go with plan B. Plan B says, well, what if u equals the secant of x? Du then is secant x tangent x dx. So now I'm going to pull a secant and a tangent off to hang out with the dx. So I'm going to make it, let's change colors to really emphasize what we're doing. We're going to pull off one secant, pull off one tangent. So we have secant x tangent x dx. All of that's going to become my du. When I pull off a secant, I'm left with secant squared. When I pull off a tangent, I'm left with tangent to the fourth. Can we make this remaining stuff all into secants? Yes, because these are already secants, and if tangent has an even power, we can change it to a Pythagorean identity. We're going to write tangent. We're going to think about that as tangent squared squared. That way, tangent squared can become secant squared minus 1. Once I've made that change, changing tangent squared into secant squared minus 1, the even exponent on the outside of that, then we can make this u substitution that we set up that we've been trying to get. So now we've got the integral of secant becomes u, secant squared minus 1 becomes u squared minus 1 squared, and secant tangent becomes our du, and this integral is going to be much easier to handle. First thing I'm going to want to do with it is do the exponents, order of operations. I can square it. Becomes u to the fourth minus 2u squared plus 1 du. Then I'm going to distribute that u through. When I do, I get the integral of u to the fifth minus 2u cubed plus 1u du. And then sure enough, this just integrates using that power rule. So we've got u to the sixth times 1/6 minus u to the fourth, divide by 4, 2 over 4 gives us 1/2, plus u squared divided by 2, plus our constant. All right, let's finish this off by going back to our u's. Every u is a secant of x, so we've got 1/6 secant of x to the 6th power minus 1/2 secant of x to the 4th power, plus 1/2 secant of x squared, plus a constant. We've got our final solution. That's how I would go about integrating when I've got secants and tangents raised to some exponent. Now, again, don't memorize the rules, way too much work. Simply say u is either going to be secant or tangent. One of them is probably going to work. The other one probably won't work. Sometimes they both work. As soon as you find one that works, though, go with it. Pull off the du and see if you can make the remaining stuff into u's. That's the general strategy. We've got a request to take a look at some convergence and divergence tests. That's a great topic to move into. I know a lot of your AP calculus classes are getting into that topic. So let's take a look at converging series next. Now, the truth is there's about 7 different convergence tests that we work with. And so we're not gonna have time to go through all 7, but let's take a look at a couple of them. Let's see about taking the sum as n goes from 1 to infinity of, let's do 1 over n squared plus 1. Couple ways you can approach this one. You can use the integral test. You can use the comparison test. I'm going to try the limit comparison test for this one. And if there's a specific, did I drop a square on the secant in the red line? Oh, at the very end, I didn't put the square on it. Sorry about that. Yeah, you're right. Needed to be squared. Can I explain? So we're going to do this with the limit comparison test just to see it. But like I said, this one can be solved using lots of different methods. And it doesn't really matter which method you use on the AP Calculus test or probably on your chapter test for your calculus classes at your colleges. So let's solve this first using the limit comparison test. The limit comparison test says we're going to take the limit as n goes to infinity, and we're going to divide it by a known series. There is a known series that's really similar to this. It's 1 over n squared. Very similar to 1 over n squared plus 1. The goal is if this goes to 0, then both of the series will converge. We know this one converges, that one converges. If it goes to infinity, then both of these need to go to infinity, but this one doesn't go to infinity. We know it converges, so that's not going to work. So our other option is if it just goes to any number, which is best, because if it goes to any number, they will both do the same thing. So let's evaluate this. We're going to multiply by the reciprocal. So I've got the limit as n goes to infinity of, multiplied by the reciprocal, sticks an n squared on top over n squared plus 1. And when n gets huge, this plus 1's really not going to do much. So we're going to end up with the n squared over n squared, which reduces down to 1. Since it reduced down to something that was not 0 and not infinity, that's best. That means these both do the same thing. Well, this one we already know that's a p-series that converges, which means our numerator, the series we care about, also will do the same thing. It converges. Let's solve it one other way, though, just to really emphasize the different ways that we can go about solving a series, decide if it converges or diverges. Let's solve it using the integral test, because this one's got an interesting interval. The idea of the integral test is if we integrate it from 1 to infinity, dn, both the integral and the series will do the same thing. They'll either both converge or they'll both diverge. Well, we know we actually proved this at the beginning of the hour. Some of you were here for that. We proved that this integral is equal to the tangent inverse of n. And so we're going to evaluate that from 1 to, well, b, where b is approaching infinity. We'll take the limit as b goes to infinity. Which is going to require us to remember what the graph of tangent inverse looks like. Do you remember what the graph of tangent inverse looks like? The graph of tangent inverse starts off flat, comes up, and then flattens off at these asymptotes. Those asymptotes are at negative pi over 2 and positive pi over 2. So when we want the tangent inverse of b, as b goes to infinity, we're asking what's happening over here at infinity? It's approaching pi over 2. So we have pi over 2 minus, plug 1 in, the tangent inverse of 1. And this is an ugly number, but it doesn't really matter. What matters is it's a number. It's not infinity. So that means this integral converges. And the integral and the series will do the same thing. So the series also converges as well. That is the integral test. Someone had a great comment, though. You could also do a direct comparison test. Yes, let's look at how a direct comparison test works with this one. Now, it turns out most series that you work with can only be solved using one method. This series is going to be nice enough to us that we can solve it using at least 3, possibly many different more methods. All right, so direct comparison. I can compare this directly to a known series 1 over n squared. To make it really obvious what's happening, n squared is definitely smaller than n squared plus 1, right? Because if I add 1, the number gets bigger. It doesn't matter what n is, adding 1 gets bigger. If I take the reciprocals of both of those, reciprocals will flip the inequality. It's like saying 100 compared to 2. If I flip it, 1 over 100 is definitely smaller than 1/2. Flipping it flips the inequality. So we'll flip this n squared to become 1 over n squared. That's going to be bigger than 1 over n squared plus 1. Now, some of you might have been able to just look at this and been like, certainly that's bigger. 1 over n squared is bigger because this is dividing by something smaller. And dividing by something smaller will make it bigger. So this one's definitely bigger. However you want to do it, I like to kind of show step by step to make it really clear what happened, how I know that 1 over n squared is bigger. But what's nice with this direct comparison is I already know this converges. If this side converges to a number and we're going to something smaller than that, then that smaller thing must also converge as well. So that is how you can show that these series converge. We did the comparison test. We did the limit comparison test. We did the integral test. There's also the alternating series test. There's the power, not the power series. There's the the ratio test and the radical test. There's also a telescoping series. Lots of different things to practice, and you could spend really a whole week going through all of those. But we looked at 3 of them here in our lives, so I think that's really helpful. Great point came up. 100% correct. Tangent inverse of 1. I said it's an ugly number. It is an ugly number. It's pi divided by 4. Because if I look on the unit circle, tangent is y over x. Y over x equaling 1 means they're exactly the same. So yes, tangent inverse is pi over 4 at 1. But that's still not a pretty number. And it doesn't really matter what the number was. Remember, with the integral test, we don't care what the number is. We just care that it is a number. And that means that it converges. We got time for one more question. And the question that just came in wanted to look at some L'Hopital's rule. So let's do some L'Hopital's rule and take the limit as x goes to infinity of 1 plus 1 over x to the x power. Hope we have enough time to do this one. We don't. Let's make it a little simpler. Let's just make it x squared over e to the x. Let's make it e to the 2x, just for fun. The idea of L'Hopital's rule is as x goes to infinity, this numerator x squared goes to infinity. This denominator, e to the 2 times infinity, also goes to infinity. And when we have infinity over infinity, it could be anything large or small. So what we have to do is use L'Hopital's rule, which tells us that we can take the derivative of the top, which gives us 2x, divided by the derivative of the bottom, which is 2e to the 2x, and that has the same value. Well, this one, if I look at this and make x go to infinity, 2 times infinity is infinity. 2 times e to the infinity is also infinity. We're still going to infinity over infinity, which means we use L'Hopital again. So we take the derivative of the top and bottom. The limit as x goes to infinity of 2 over, take the derivative of the bottom, we get 4 e to the 2x. And now when I plug in infinity, what we notice is we end up with this denominator getting huge. 2 divided by huge is going to be 0. So in this case, this limit is going to 0 using L'Hopital's rule. Oh, and it's too bad the integral of 1 over x to the 5th plus 1. We just don't have time to get to that one. I am so sorry. But I do have a TikTok on my page, on my Instagram page, a reel of me solving it. It took me 48 minutes solving it by myself. That's a beautiful problem. But we don't have time for that here. In fact, we are wrapping up. We're just about out of time. And I want to give a huge thank you to all of you for joining me today. Thank you. It's been a pleasure sharing my love of calculus with you. The questions and interaction have been great. Hopefully it's been helpful to you. But before we go, don't forget to check out chegg.com. We are here all semester long to support you 24/7 in your toughest subjects, including calculus and your other tough subjects. Make sure you're, of course, also following Chegg here on TikTok, Instagram, Twitch, YouTube, all of the streaming places. We're happy to have you here to help you learning more content like this. We are here every week at this time to help you out with your calculus questions. So mark your calendars, scan the QR code so you don't miss future lives. And until then, happy studying, everybody.